Hey guys, it's Luke here, and today we're going to talk about asymmetric synthesis, or rather how we can determine what sort of isomer or enantiomer we've got in a mixture. So as you can see here, we're going to consider a racemic alcohol. In this case we're just going to use phenol, pretty much, almost. And as you can see there are two different enantiomers of phenol. As this question says, how do we tell if we have a single enantiomer? And we can do this by measuring the enantiomeric excess, and that's the percentage of the major enantiomer minus the percentage of the minor enantiomer. So, for example, in a 4:1 mixture, it's 80% of the major enantiomer and 20% of the minor enantiomer. So the percentage EE is 80 minus 20, which is 60. So there's a few techniques that we're going to go through which show asymmetric synthesis and how we can determine these EE values, and how we can see which one we've actually got in the mixture. So there's this thing called optical rotation, and this is basically a definition of what an enantiomer is. They have the same physical properties except the direction in which they rotate plane polarized light. That's effectively what an enantiomer is. So we can look at polarimetry, and what happens here, you shine a bit of light at a filter, that obviously selects the wavelength of light that you're going to be using. That then goes through your sample, it goes through another filter at a certain angle, and then that comes out and you see the eyes. You see it at your eyes. So unfortunately in this technique we need to know what the rotation of the pure material, which obviously can't be predicted, so we need to know that before we do this experiment. Sometimes we won't be able to know, but for a known material we do the angle, and then using these conditions, which is the NAD line here and the temperature, and then we divide that by the enantiomer pure sample and then times it by 100 to get the percentage. We can also look at chiral shift NMR. We can use chiral Lewis acid additives to create diastereomeric complexes and use NMR to get a ratio of how much we've got, etc. So as you can see here, we've got the same sort of phenol. We're going to use EU FOD 3. We've used FOD before. That's pretty much what it looks like, and obviously we're going to add EU FOD to it in place of a on top of the O. We're going to add it to the oxygen, and that's obviously going to create two enantiomers. If we look at the chiral mixture, that's the racemic mixture just on the left there, which is that one up there, and this is when we've got a 4:1 ratio, e.g. 60% EE. So that's what we make. We basically make a 4 ratio of this product and a 1 ratio of that product, and that just shows on the NMR shifts. Now unfortunately in NMR the lines can get broadened, which makes it harder to read, obviously, making the calculations for EE less accurate. So obviously everything's got a good and a bad side to it. And finally, chromatography using the chiral absorbents. Enantiomers will bind to these chiral absorbents, and the weaker complex pass through the column a lot quicker. So obviously you can plot a graph of time and see how fast things travel through the complex. There's a 4:1 mixture. We've got one molecule passing through after a slower time, which is 20% of the enantiomer, and we've got another molecule passing through at a longer time, which is 8% of the enantiomer. And that's just the techniques you can use to determine what one you've got. Next video we're going to be looking at some chiral reagents and stuff as well.